So, dear students, today we have come here to discuss one more special problem in kinematics of rigid bodies. You remember that in our last class we had discussed about the absolute motion analysis method of finding the velocity and acceleration of a rigid body or a system of rigid bodies. In continuation to that particular discussion, today we will take up a special problem. This problem finds an important application in the different engineering examples. So this is basically called the rolling without slipping problem. So this is a special problem in the sense that it is what is called as a rolling without slipping. So this is the exam. This is very important. The type of motion that a cylinder or a sphere-like rigid body will execute. So this is actually termed as the rolling without slipping, or sometimes it is also known as ideal rolling condition. Ideal rolling condition. And whenever we have the rolling motion problem, if nothing is mentioned regarding the type of the rolling, we will always assume that this rolling is basically the perfect rolling motion. It's ideal rolling problem. So we will always assume actually in that particular direction. So this is the general arrangement of the problem. Let us try to explain what is the general arrangement. Here we can see that there is a arc-like path whose center is at the point O and whose radius is actually radius of curvature of this path is capital R. And we have a cylinder or a sphere-like rigid body. This is the rigid body basically, whose radius is R. Now, suppose this cylinder or the radius-like rigid body rolls over this curved surface. Rolls means that it will execute both translational motion and the rotational motion. That's a general rolling situation. So what happens is that as this sphere or cylindrical like rigid body rolls without slipping on this particular surface, we note that the thing will move actually in this manner. So it will go and move in this direction. So we note that on this particular rigid body, let us identify a point B on the body, on this cylinder or the sphere-like substance, which is making an angle phi with the radial line CA, correct? And we try to find out. The problem is that here this point B is at a distance of rho from the center. That means CB is rho, and the angle, the coordinate that it is having with respect to this initial setting line, this line we can call as to be the initial line OA, along which we have put our coordinate reference frame as well. We fix up the inertial reference frame X and Y with its origin at this point A, and we assume that this line OA is aligned along this Y axis, from where we actually try to locate the point B on the body. So this is the this is where we have. Now let us suppose that this distance CB, we call it rho, and the radius of this sphere or cylindrical like substance, rigid body, is, we take it to be equal to small r. So we assume that, so as the the body rolls in this direction, so it's rolling in the clockwise direction when you are looking it from the front. So we notice that when it rolls in this manner, correct, it is rolling up the plane. So it rolls up the plane. So as it rolls up the plane, we note that we find from here that as the the substance is rolling in this direction, we see that it comes and occupies this particular situation. So this is the position it will occupy, correct, in this position. And let us suppose that what we are getting is this, that by doing in this process, how we can come to this particular position after some time. So what will be our objective? Before going into this description, let us try to clarify what is going to be our problem. Now our problem is that if we take a general point B on this body, we try to calculate what will be the velocity. That means our objective here will be to calculate, obviously to calculate the velocity of point B. So let's take this velocity of point B and acceleration of point B. So this is what we are going to calculate at this position. That means at when we say when theta is equal to 0. Theta, you see the amount of the displacement, angular displacement that this rigid body can have while it rolls up on this curved surface. So this is actually we try to calculate. That is, this is our basically, the problem is this one. That means we need to calculate the velocity and acceleration of this point B when this body is at the position theta equal to, when the body is at the position theta equal to 0. That means when it is in this initial condition. So we assume the condition of this body after some time delta t. That means we take this after time delta t. Let us suppose that this rigid body comes to this location, and we see while coming into this location, the center point C of this cylinder actually moves from the location C to C prime. So this is where the point goes. C, from the point C, if the center of this body, cylinder or the sphere, it moves to the location C dash. And while it describes this, this location, it goes to this position along this circular path. There is a, this circular, we can consider a circular arc like this. So as it travels, which will be parallel to this path, of course. So as it travels to this CC prime position, it describes this angle theta. So the actually the arc length that this center of the sphere travels is basically equal to what? So we can say the arc length that the center of the cylinder travels, we can write it as CC prime, and this arc length we can write it to be equal to capital R minus, we can say that the arc length, not say CC dash, let us consider not the arc length traveled by the center. Let us consider the arc length traveled by the point A, which is the point of contact of this cylinder at initially. So initially this cylinder or the sphere like substance is making a contact at point A on this curved surface, on the curved path over which it is rolling, and after time t, delta t, let us suppose that this point goes to the position A prime. That means we can say that at that location we see the arc length traveled by the point A will be obviously equal to, so we can say the arc length AA dash, we can say the arc length AA dash, that will be equal to, we know that it will be equal to capital R into theta. Okay. Now, in order to arrive at this position, we can mentally think, since this is a general plane motion, that means we can, as per the Chesel's theorem, we can conceive this motion to be a combination of curvilinear translation and rotation. So this takes care of the translational movement of this point. So this is the amount of the arc length it travels. So we see that when it comes to this, we just mentally, we just mentally bring this cylinder or the sphere-like substance just by dragging it over the surface and place it here like that. So in doing so, we note that it travels this much amount of distance, correct? Now, but this is not the desired position. The desired position is what? Now, while it moves in this way, it actually rotates about its own center, because that will only consist of the total rolling motion of this cylinder or this sphere-like substance. So what we do? Now, because while we have taken it from this position to this position by dragging it over this curved surface, we see the point A comes to the point A prime, and the center of this cylinder or this sphere, whatever is this rigid body is, it actually moves along this, along this parallel path, and moves along this circular arc, and moves from the initial position C to its final position C prime. So this is basically the curvilinear translation. So as the point A takes to the position A dash, the center moves along the parallel path and comes to the location C dash. And while doing so, the actual distance over the surface of this path is covered by the point A, and it is equal to R into theta. But while coming to this location, we find that the center C has come to its desired location. But if you note that while it rolls, you'll see that the point A will not remain in this position. Correct? So what it will do, it will move towards the left because of the rolling action. Because the sphere is rolling in the forward direction or towards the rightward direction, this line segment CA will rotate and will come to the location. Suppose it is here, the location we call this location as CA prime. So this is the line position. Actually, the final position C dash A dash is the final position of the line segment CA. Final means after time delta t, when the body comes from this position to this position. So the line segment CA, which was initially there, is now coming to the position C dash A dash. And we can think the transformation from this CA to C dash A dash as a combination of curvilinear translation plus rotation, in the way that I bring the location of the center to its desired location, that means C dash position, and then since your point A has not come to the position, its proper position, so what it is to be done? Now at this point you just give a rotation so that this line segment C dash A, right, C dash A comes to its desired location, that is C dash A dash. That means this angle of rotation, that means what I try to say is this angle, I mean to say the angle AC dash A dash. We suppose that this angle AC dash A dash, let that be equal to let this be equal to phi. Let this be equal to phi. Now, since when it moves in this manner, that means in the rotational part, this is the pure rotation, it is taking place with respect to the point C dash as per our Chesel's theorem, and we find that the radius C dash A has been rotated by this angle phi to come to its final or desired location, that is C dash A dash, and in doing so it actually generates some angle, and we call this angle as phi. So while this rotation takes place, we see that the arc length AA prime that we are getting, the arc length AA prime, because of this rotation, becomes equal to how much? Now it becomes equal to smaller into phi, because we have assumed the radius of this body has to be smaller. So as far as the perfect rolling or rolling without slipping is concerned, it means that this is the translational part that the rigid body is having, correct? The point A is moving to this AA dash position. That means we can say this is A double dash. Let us call it as AA double dash, the intermediate position. And we see that this AA double dash, this comes out to be equal to r theta, and as a result this will be A double dash, this angle A double dash C dash A dash is equal to phi. So we can say that the arc length A double dash A dash, that becomes equal to r into phi. So as this rolling without slipping is concerned, we can say that these two distances must be equal. That means the amount of translational motion must be equal to the amount of the rotational motion. So this is the distance traveled due to the translational motion. This is the distance traveled due to the rotational motion. Because of the perfect rolling condition, these two should be equal. So for perfect rolling, so we can therefore write from here that for perfect rolling condition, we can say that for perfect rolling, we can write for perfect rolling condition, we must note that perfect rolling condition, we must note that capital R into theta, that must be equal to, we can say this is capital R theta must be equal to smaller into phi. So this is actually, the perfect rolling situation will demand for this particular condition to be true. So it shows therefore the translational displacement and the displacement due to the rotation, they should be actually equal to each other. So that is the condition for the perfect rolling situation. Now we see that while it goes in this manner, what will be the angular velocity of this body? Because it not only has the translational motion, it also has the rotational motion. So we note that, you see here from here, we note that with respect to this initial line, correct? So with respect to this initial line, if we think that we know that the angular velocity is generally measured by means of the calculating the orientation change of the body. So what we notice from here is that the net change in the orientation of the body, correct, will be what? The line CA, that means this line which is the radius of course, is the angle this radius is making with respect to the reference line. So this was the reference line, and since it was aligned along this reference line, obviously initial orientation is 0. Now after time t, if we suppose when this body comes to this location, we note that the orientation, that means this radial line now makes the angle with respect to this line, I mean to say with respect to this fixed reference line, which is, you know, is this line. How much will be this angle? So it is pretty clear that this is going to be the angle. That means the angle A dash C dash, and if we say we take this here some point, let's call it say point D, then it will be A dash C dash D. This angle will give the orientation of the radial line with respect to this fixed line. So in other words, the orientation here, that means is this much angle, will be definitely equal to how much? Now that is going to be equal to phi minus theta. So it is going to be equal to phi minus theta, because you see this angle is phi, right? This is the angle of rotation, and since this angle is theta, so definitely this radial line therefore will make an angle phi minus theta with respect to this fixed reference line. So differentiation of this with respect to time definitely will give me the angular velocity of this body. So if we suppose that the angular velocity of this body is omega, then we can say that omega is basically equal to, we note from here that omega is basically equal to phi dot minus theta dot. Remember, phi r theta is equal to r into phi. So we can at least write from here that from here we can say that phi will be basically equal to r by capital R into theta. So that is going to be equal to the angle phi. So phi dot minus theta dot. So in place of this we can substitute and can say that this will be basically equal to r by r minus 1 taking common, and we get that this is basically equal to theta dot. So from here we can say that theta dot, we can write from here that theta dot, that is equal to how much? Now that we get from here is r into omega divided by capital R minus small r. So that is going to be equal to theta dot. And obviously it will give us the value of phi dot as well, and the value of phi dot, which will be equal to r by r into theta dot. That means we need to multiply this quantity by capital R by small r, and obviously we see from here that it becomes omega into r by r minus r. And here r is a bigger radius, capital R is a bigger radius, small r is a smaller radius, so r minus capital R minus small r is going to be positive for us. So we see that this will be giving us the time derivative of the the angles in terms of the angular velocity of this rigid body. So once we get this particular scenario, once we are getting this particular scenario, let us now, for absolute motion analysis, we try to now locate the coordinates of the point B, where the point B goes. You see, this was its initial position. Actually, this distance rho is going to be constant, and the angle that this line is making, it gives me the initial coordinate of the point B. This is how I locate any point on the cylindrical surface or on the circular surface or on the spherical surface by means of this what looks like a polar coordinate system. So now I need to track the point B, that where the point B goes when the sphere or the cylinder like substance from here, when it comes to this location after time t equal to delta t, and this is, you remember, at the position t equal to 0 or the initial position. So I need to track where the point B is going. So I see, when I just let us do it in a step by step. What we did initially, we dragged this cylindrical like substance over this curved path to this position. So when it comes to this position, this line CA, which was initially aligned along this fixed direction, now comes to the position C dash A double dash. And naturally, if we do not take any further motion, actually it was at an angle of phi. It was at an angle of phi from this. It was at an angle of phi from this particular. You see the. Acha, let me change this angle. I do not say that it is equal to phi. Let us suppose that this angle is equal to psi. Sorry, we do not. Otherwise, it will be clash of symbols will take place. So let us define the point B by the angle called psi. Let us define it by the angle called psi. So obviously, what we find from here is that when the cylinder or the sphere-like substance has been dragged over this curved path to come to this desired, come to this intermediate position, we should say that this line segment CA now has been aligned along C dash A double dash position. So naturally, point B, it is we assume it to be point B here, or we can place it to be as, say, point B double dash. We can mark it as the intermediate position. So we can say label it by B double dash. This is the intermediate position of the point B, and it is pretty obvious that this total angle from here to here, it was actually equal. Oh, this angle was defined by the angle beta. Sorry, so don't require any psi angle. So let me write it to be equal to beta. So it was actually the point B was located by the angle beta here. So let us call this angle as beta. So it is obvious that since we haven't changed anything here, so when it is being dragged like that, you see the angle that this B double dash C dash B double dash position, this line will make with this this C dash A double dash, which is the intermediate position of this radial line CA. This total angle from here to the position B double dash, that means this line is aligned along this B double dash position. We note that this angle will be obviously remaining unaffected, and it will be equal to beta, because this is this is a fixed line and this is a fixed line. So angle between them is going not to be changed, obviously, because of the everything. So obviously this angle is going to be equal to beta, but we have to remember that this B double dash is just in temporary, or what should I say, that the intermediate position in our Chesel's theorem description of the motion. So what we need to do, that coming at this position, what we have done really, actually, in fact, after coming to this position, what we have given? We have given this cylinder a rotation by an angle of phi with respect to the point C dash, as a result of which the radial line C dash A double dash has come to its desired location C dash A dash, and we call that angle as phi. So naturally, this radial line C dash B double dash will be rotated by the same angle, because it is the rigidity concept. So it will rotate by the same angle called phi, and thereby will come to its desired location, which is B dash. So now the desired location of this radial line CB, because of this whole rolling motion, is actually this line segment. So we are having this this position C dash B dash, and the angle between them, that means angle between B dash C dash A double dash. So we can say the angle between, so we can write from here that this angle between, we can write it like this. We can say that angle between B double dash, C dash and B dash, this is going to be equal to phi. So the rotational component of the total general motion, or in the descriptions of Chesel's theorem, this is the thing. You remember that this theta defines the curvilinear translational parameter in the description of Chesel's theorem, and the angle phi, that actually defines the rotational component of the motion in Chesel's theorem's description. So naturally, this angle B double dash, C dash and B dash, this angle is going to be equal to phi. So if we now track the coordinates of this B dash position, right, the coordinates of the point B after delta t time, when it describes by an angle of theta, when it comes to this location, we see that at this position, what will be the coordinates of this point B dash with respect to this inertial reference frame? Because we need to move by absolute motion analysis. That means we need to measure all the positional coordinates of the desired points or the desired lines. Their positional coordinates need to be calculated with respect to an inertial reference frame. In this case, our inertial reference frame is XAY with its origin being placed over here. So this is where the origin is. Now with respect to this coordinate reference frame, we are trying to locate the coordinates of B dash. So how that can be done? So obviously the B dash point has some X coordinate which will be measured from, say, if we take a mentally, if we take a line here, say we draw a line like that, so this is the line, and from here this is the line, we can say this is the origin, so this is the line. So the distance between these two lines, so distance between these two lines, so this is going to be equal to our XB. So that is going to be equal to our XB. So how we are going to calculate this XB? Now that is simple. So let us try to first find that this is going to be our XB, and what will be our YB dash? Not only it is having the X coordinate, it is also having the Y coordinate. So Y coordinate will be, just take this line from here, and I just try to show it by means of a very thin line so as not to clutter the drawing much. So you see this is the B dash position. So this is the B dash position. Let us take this line from here, B dash. That means we draw a line, parallel horizontal line with this x-axis. We draw this line, and obviously this height between this one and this one will define the Y coordinate of the point B. So let us call this as YB dash. So we have XB dash, so we can call it as XB dash, and another one we can call it as YB dash. That defines our coordinates of this point B dash. So we say from here that what will be the coordinates of XB dash, of X coordinate of the point B dash. So we can say from here that XB dash, we can say that XB dash will be equal to how much? So that will be obviously, this distance, correct? So from here to here, C dash distance, this distance, that means XC dash, we can say, and XC dash is definitely going to be this much distance. This is going to be XC dash. This is going to be our XC dash. So we can say that this XC dash will be equal to how much? Now that is pretty simple. How much it will be? If you drop a perpendicular from C dash onto this line, so that means if we draw a perpendicular like this, okay, let me draw it with a different color so that we can understand it. So you see that if we draw this perpendicular from here, then definitely this perpendicular is going to give us the value of XC dash. And how much will be that value? So obviously it will be OC dash, right? XC dash will be equal to how much? That is going to be equal to OC dash. We can say that it will be going to be equal to OC dash. So we just say this is OC dash cos theta, OC dash sin theta. So OC dash sin theta plus, because we need to go further. So how much we need to go further? We need to go further by this much distance. And how much will be this much distance. I mean to say this much distance we need to go further. So how much will be that? So obviously then we need to find out the angle made by this C dash B dash line with respect to this reference line. So that we need to do in a very step-by-step manner. So how much will be this angle? So we see that the angle, this line OA double dash is making with respect to this vertical line is going to be equal to theta. So that is going to be our angle. So we just write this angle, that is going to be our angle theta. We need to calculate the total angle made by, that means we need to calculate the angle made by this line, right? So that is going to be equal to, you know, this is theta plus we need to calculate this much angle. So how much is this? That is going to be equal to beta minus phi, because from here to here this angle was beta and we then backtracked by an angle of phi. So it will be therefore theta plus, we can say it is going to be theta plus beta minus phi. So that will be the angle made by the line segment C dash B dash with respect to this vertical line which is parallel to this fixed y-axis, correct? So that is, you know, this angle. And you see that we need to calculate sine of that with respect to this radial line. So what we need to do, we need to take sine of this. So just we push it little bit here. So it will be therefore, you know, that it is going to be equal to it is going to be equal to rho. So this distance rho into sine of this angle. So that means sine of this angle. That means it is going to be equal to rho sine theta plus beta minus phi. So you see, you can very easily calculate what will be the coordinates of this point B dash, right, with respect to this line. Now you need to see how much is OC dash. So OC dash is clearly, you see from here that OC dash is going to be equal to, that is going to be equal to how much? That is going to be equal to capital R minus small r, or OC dash that will be also equal to OC in fact. So OC dash is also equal to OC. OC means this line. So we can say here, we can write from here that OC dash is equal to OC and that is equal to capital R minus small r. So we can write it in this way. So therefore we can say from here that our xb dash, that is going to be equal to, we can say finally that it will be r minus small r into sine of theta plus it will be rho into sine of theta plus beta minus phi. So that is going to be our x coordinate. So we just label it, finding out that this is going to be my x coordinate of the point B dash after the motion has taken place, and we say that this is our x coordinate of the point B dash. Now we are trying to calculate the y coordinate of the point B dash. So we can say now y for the y coordinate. So we can say now yb dash, that means the y coordinate of the point B dash, how we can go and calculate it. So we see from here that the y coordinate, you remember this is the y coordinate, we said that this is yb dash, this is our going to be our y coordinate. And how much will be this y coordinate from here? So we can calculate it in the same manner. That means we just see from here that how we are going to calculate this y coordinate. First of all, we try to locate that the height of this CA. Now here, this is the, this is the C and this is your C dash. So we can say from here that the y coordinate from here is going to be equal to. So we note that how much will be this. So we see from here that we need to calculate the height between C and C dash. Correct. So height between C and C dash, that means basically we try to calculate this height. So we just say it like that. This is the height that we need to calculate. So how much is that height? So how much is this height? So we can calculate it very easily. So that will be, here this total distance was r minus r. This total distance was r minus, because this is OC, correct? And from here to here, from OC to, I mean to say the, if we call this as say point D, then OD, because O is the center point here. O is the center point here, we come. So this is the center point. So OD is capital R minus small r cos theta. And this total is capital R minus small r. So naturally, if we subtract these two, then I will be getting this height. That means the height of the C to C dash. So that height we can very easily calculate from here. So that is going to be our height. So we can say from here is that we can write that YB dash is going to be equal to, sorry, we can write it in this manner. We can say that this is going to be equal to capital R minus small r into 1 minus cos of theta. So that is going to be our height from the point A to the sorry, because we are trying to calculate the height from here only, right? So we are trying to calculate the height from here only. So we need to add to it. We need to add to it, because this distance is this height we have calculated as capital R in minus small r into 1 minus cos theta. That is going to be this height, but we need to add to it the r, because our origin is here. We need to calculate the origin here, because we see that our origin is here. So we need to calculate the total height from A to C dash. This height will be, we need to add to it the distance small r. So we just add to it the distance small r, correct? So if we add it, then we will be getting directly the height of C dash from point A, right? And we need to calculate the height B dash of the point B dash from this line. So how much is this drop? See, you if we just note from here how much will be going to this drop. Now this drop will be going to be definitely equal to, this is going to be equal to, this is rho, and we see that because this is going to be equal to rho, this is going to be equal to rho, and this red arrow, this red angle is equal to theta plus beta minus phi. So naturally the height is from here rho cos theta plus beta minus phi, and that too in the downward direction. So it means it is below the C dash point, right? So it is in the downward direction. So I need to subtract from here and write that it should be rho cos of theta plus beta minus phi. So that is going to be the coordinate, y coordinate for the point B dash. So let us try to see these coordinates, because these are very important. You need to define the coordinates well, and the coordinates, how it is being defined, it is defined step by step. Let me once again explain to you how we are going to calculate the coordinate of the y coordinate of this point. We are doing it with respect to point A, remember, because this is where our origin is. So actually what we have done, firstly we calculate the height of the C dash from point A. So that is going to be equal to how much? So you see the relative height between these two center positions is definitely equal to r minus small r whole into 1 minus cos theta. So that is going to be this relative height. That means this pink height. So this pink is basically equal to this pink dimension So if you see this pink dimension is basically equal to capital R minus, so we write it in this way. Let me say it in this way. So this is going to be equal to capital R minus small r whole into 1 minus cos theta. So that is going to be this pink dimension. So that is what you need to add to it, the distance r, then you will be getting the coordinates of c dash, y coordinate of c dash from point A. Correct? Now you need to come down, because you see the point B dash is here and this angle is there. So you need to calculate the height of the projection of this B dash point on this line, vertical line. So the projection is in the downward direction. So therefore the resultant coordinate of this point comes out to be in this manner. So it is going to be our y coordinate of the point B dash. So once we get these are our coordinates, we now can differentiate these two coordinates with respect to time in order to find out the velocity for the point B dash. So definitely, since your point B dash has both x and y coordinates, so definitely the point B dash will be having both components of velocity along x direction as well as along the y direction. So we can therefore say the x directional velocity, we can write that it is Vx point B dash, that is going to be equal to, obviously this is going to be equal to dx B dash dt. Correct? So you need to differentiate this equation with respect to time. So if you differentiate it with respect to time, you are getting it, this is to be equal to r minus r into cos theta into theta dot. Correct? Then we have plus, this rho is constant. So first we differentiate this theta plus beta minus phi. Then remember this beta is constant. So you need to differentiate the remaining angle. That means theta dot minus phi dot. Correct? So the angle turns out to be something like this. So if we simplify, this becomes equal to, you now put theta dot. Theta dot is obviously equal to omega into r minus r. So theta dot r minus r is basically equal to, so these two will be clubbed together. Capital R minus small r into theta dot will be clubbed together, and it will become equal to omega into r. So we can write this is equal to omega into r into cos theta. Correct? And now theta dot minus phi dot. You remember phi dot minus theta dot is omega. So I just take a minus sign from here and can write that it will be minus rho omega into cos of theta plus beta minus phi. So that is going to be my Vx B dash. So this is equal to, we can say Vx B dash. But please remember, we need to calculate the velocity of the point B, which is in this initial geometrical position. But what we are going to calculate is the velocity of this point B dash in the deflected geometry after time delta t. Correct? From the initial time. So we need to backtrack this geometry. We need to backtrack this geometry from this position to this position. But we cannot analyze it from this position because it is a given initial position. So we cannot apply, we cannot formulate any equation for this position because this is a the instantaneous position. So what we need to do, we need to first of all find a general situation. So general configuration or the general position of this cylinder or this sphere-like substance. Find out the general coordinates and then we need to backtrack. So we'll come and show you how the backtracking is done later. So you see this is going to be equal to Vx B dash. So what we do at this stage, we insert one more page here. So we can say from here is something like this. So we have got this particular expression for Vx b dash. And similarly, if we differentiate it further, we will set our stage for finding out the acceleration also. So you need to differentiate once more and can write that it will be equal to, since your omega can vary, so naturally omega can be function of time. So we can write this will be omega dot r into cos theta, correct? Then we need to differentiate this. So again it will becoming minus omega into r theta dot into sine theta. So we can say this one. Similarly, coming here we can have minus rho omega dot. This will be cos theta plus beta minus phi. And then again we need to differentiate. This time it will become plus. So it will become rho into omega sine of theta plus beta minus phi. And then again we will be having into theta dot minus phi dot, this thing. So if you further simplify it, it can be therefore omega dot into r into cos theta. Now you remember we have found theta dot expression, and theta dot expression is omega r by r minus r. So we just substitute that omega r. So it will become therefore omega minus omega square into r square by r minus r into sine theta. Then we have minus rho omega dot cos of theta plus beta minus phi. And then we have, since phi dot minus theta dot is omega, so I put a minus sign here, make it minus rho omega square sine of theta plus beta minus phi. So that is going to be my x component acceleration in the general coordinate, general configuration of the body. Now once this is done for the velocity and acceleration, now we come to the y component of the velocity and acceleration. So we need to differentiate this y coordinate also. So what we can do from here at this stage, what we can do from here is something like this. We can say therefore v y b dash, that means the y component of the velocity of the point b dash is going to be equal to, this is capital R minus r into 1 minus cos theta, so it becomes plus. So it will be r minus small r into theta dot, once again into theta dot. This will become plus sine theta. This r will not be there definitely, so it will become plus rho into sine of theta plus beta minus phi, again into we have theta dot minus phi dot. So that is the thing. So if we further simplify it, remember this theta dot expression. So once again we just remember this expression, theta dot r minus r theta dot is smaller omega. So again we can have that privilege. So it becomes omega into r into sine theta. And since this is equal to minus omega, so we put this is minus omega into rho into sine of theta plus beta minus phi. So that is going to be my y component of the velocity of the point b dash. So this is our y component of the velocity that we have found. So we have therefore, here we have found one expression, and this is another expression of the velocities. And here we have a big expression for acceleration. Let me label it with a different color. So this is the acceleration expression, and we again find out the acceleration expression for our y component. So we need to differentiate this equation to find out the acceleration of the point B dash. So we differentiate, remembering omega can vary, so it will be omega dot r sine theta. Then we have plus omega r theta dot into cos theta. Then we have minus omega dot into rho into sine of theta plus beta minus phi. Then we have minus rho omega into cos of theta plus beta minus phi into, this will be theta dot minus phi dot. So we have this expression, remembering again that theta dot minus phi dot is minus omega. I have omega dot r sine theta, and again you remember that theta dot is equal to omega small r by capital R minus small r. So we can put it here. We can say this will be omega square r square by capital R minus small r into cos theta. Then we have this expression minus rho into omega dot into sine of theta plus beta minus phi. And then we see, since we have this one, phi dot minus theta dot is, or rather theta dot minus phi dot is minus omega, so we can say it is plus rho omega square into cos of theta plus beta minus phi. So this is going to be our expression. Very complicated, no doubt about it, and difficult to analyze are the two expressions for the accelerations. But again, we need to stress onto the fact that we have calculated the velocity and acceleration of this point B dash when it has come, it has come to this location, and we have calculated the velocity here on this body at this position when it has traveled by this distance theta. But we have been asked to find out the velocity and acceleration of this point B, that means this initial position of this point. At that initial position, what should be our velocity and acceleration of the case? So I need to therefore bring back this geometry to this position. And how this bringing back will be done mathematically? Just by substituting theta equal to 0 in the above expressions. So whatever we have got here, and need to remember that if theta is equal to 0, then by this equation, you see, by this equation, phi must also be equal to 0. So therefore, we need to put both theta and phi to be equal to 0 in our above expressions. So therefore, we can write that, therefore, at the initial situation, so at initial position, we can say at initial position, we note that both our theta and phi, both theta is equal to 0 and also phi is also equal to 0. So if we remember that, then it implies from here that the velocity of the point B now, so instead of B dash, now it becomes the point B. So Vxb. So from B dash to B, this transformation has taken place by substituting in place of theta and phi, both we have substituted to be equal to 0. So if we put this here, theta equal to and phi equal to 0, then what will happen to this expression? So it will become omega r cos theta. So we can see this becomes omega r cos theta, and then it becomes minus rho omega. Oh, sorry, cos theta is 0. There, theta is 0, sorry. So it becomes 1 only. So it is not cos theta. So it will be omega r only. And then we have minus, this will be rho into omega, rho omega. and theta and phi both 0, so we have beta only, so it is cos beta. Or we can write it in this manner, omega taking common, it will be r minus rho into cos beta, correct? So that is going to be my velocity of the point B at the initial position. So this is very important. At the initial position, this is the situation. So this is the x component of velocity of point B. Similarly, we have y component of the velocity of point B. What will be its status? So in this expression, we are going to put theta equal to 0. Remember, theta equal to 0 and phi equal to 0. So if we substitute, then we find that this component does not exist. And then we have minus rho into omega into sine beta. So we find therefore that these two are therefore the components of velocity of the point B in the initial position. Since your r, we have assumed it to be greater than rho, because rho is it is the inside point on the cylinder or the sphere like substance. It may be the outside point also. You can actually, by varying rho and beta, you can take any point either inside the domain of the cylinder or the sphere like substance or outside, even on the circumference of the body. So that is the beauty. That means you control this parameter rho as well as beta, and you will track down every possible point on or inside or outside of this body. So that can be done by doing this manner. For example, if we try to calculate the velocity of the point A at the initial position, what will be the velocity at the point A in the initial position? So before coming to the initial position, let us actually try to calculate the velocity of the point A double dash in this general, the general configuration. So in order to capture the A double dash point, we need to do two transformations. First of all, your rho must be equal to smaller, because you need to take this inside point on the circumference of the sphere or the cylinder like substance. So first transformation that you need to do is you need to make rho equal to this. Rho is need to be taken to be equal to small r, correct? This should be equal to small r. That is number one. And number two is that your beta must be equal to 0. Your beta must be equal to 0. So if you do that, you see here in this expression, if you just do it in that way, what we have said? We have said that we need to consider this beta to be equal to 0, correct? So if we need to consider this beta to be equal to 0, and you need to consider this rho to be equal to, equal to r. So you see here, it will become omega r into cos theta minus it will become omega into r into cos of theta minus phi. So you see, this is becoming cos of theta minus phi. So from here we can calculate the velocity of the point A dash in that configuration. Now, since we are trying to calculate the velocity of the point in the initial position, so in the initial position, same story. That means you need to make your rho and r to be equal and beta to be equal to 0. So you find from here that it becomes r minus small r into cos 0 means 1. So Vx becomes equal to 0. So by the side here we can write for point A, we can say for point A we can write that Vx, right, Vx at A, this must be equal to 0. And similarly, if you come here, you can at least notice that Vy at A, that must also be equal to 0. So it means that the velocity of point A is 0. So this is very important a thing. Since you are making your motion to be, perfect rolling motion, it means that the point A, so it means that your point A, which is having